Right, carrying on our look at complex numbers and locus. What we're now looking at is functions using complex numbers. So omega will equal some function of z. So we're substituting complex numbers into functions. Now, there's only one problem with this. You see, if I'm going to substitute in a complex number, I'm substituting a real and an imaginary number into the function. So that's two values. And the output will have a real and imaginary number. That's another two values. So in fact, the point has 4 coordinates. So it's 4-dimensional. Yeah, we've got a little bit of a problem because in a 3-dimensional world, we can't draw a 4-dimensional graph. Okay? So we do it a little bit differently. We tend to have one graph for the input, and that's just in 2 dimensions, and one graph for the output. And that'll be in 2 dimensions. So the idea is we'll have some condition for omega or z. So we'll be substituting all the numbers in that satisfy some condition. And that would be our input graph. And the way we try and find out what it is, whatever that condition is, usually we just make that the subject and it'll sort the problem out. Some common ones we see, some ideas. If we're told omega is purely real, then what can I take from that? Well, I know then my answers, the imaginary part will be 0. Or if I think about the argument must be 0 or pi. So I can use those ideas. If I know the answer is going to be purely imaginary, then I know the real part is 0, but with the arguments that must be plus or minus pi on 2. This one here, that's the simplest way I can sort of write it, I guess. Argument of, and then in there you have a linear function on a linear function. So I don't know, z plus 2 on z plus 3 or something like that is equal to some angle. That locus will turn out to be an arc of a circle. That's a common sort of one we see. So I point that one out. So if you see that, we can recognise it straight away. Oh yeah, okay, that's going to be an arc of a circle. And it'll be a minor arc if that angle is greater than pi on 2. It'll be a major arc if it's less than pi on 2. And a semicircle if it is in fact pi on 2. So there are a couple of common ones. So let's have a look at this idea. Okay, so w equals z plus 2 on z. And we're going to be substituting in all the numbers where the modulus of z is equal to 4. Well, so the idea is, let's make z the subject of this, because that's what we know. We know the modulus of z is equal to 4. So let's play around with this and make z the subject. So zw will be z plus 2. Factorise and divide. So I've now got z the subject. We know the modulus of z is equal to 4, so I now can look at my answer and say, well, hang on, that means the modulus of 2 over w minus 1 is equal to 4. So there's my locus. Now, written like that, what is it? Not quite sure, so let's play around with it. So 2, well, absolute value of 2 is 2, over the modulus of w minus 1 is 4. Let's turn both sides upside down and then play with the numbers. I get the modulus of w minus 1 is equal to half. That's something I recognise. So the answer is also going to be a circle. Centre 1, 0 and radius of a half. So if I wanted to give it an equation, there it is. X minus 1 squared plus y squared is a quarter. So what we're saying is if we got all the numbers that lie on the circle, x squared plus y squared is equal to 4. Substitute them in this function, then the output would be a new circle. It'll be a circle with centre 1, 0, radius a half. Okay, let's try one of these ones where it's purely real. So the locus of z, w equals z plus 1 on z minus 1. This time the condition they've told us is w. So we can substitute z in so long as the answers we get are just real numbers. So what would the input look like? What would z look like? Well, not sure straight away, so I'm going to break it down into imaginary and real. So I get x plus 1 plus iy, x minus 1 plus iy. Realise the denominator, and what do we get? It's purely real. So if it's purely real, then I know the imaginary part is equal to 0. So a lot of this fraction I don't really need, because we're saying the imaginary part is equal to 0. So I'm only interested in the imaginary part, the bit that has I attached to it. And really I'm not interested about the bottom of the fraction either. because you've got a fraction equaling 0, we know it's the top of the fraction that must equal 0. So therefore, I'm just looking at minus x plus 1 times y plus x minus 1 times y is equal to 0. Oh, what does this turn out to be then? Well, we get, oh, look, minus xy plus xy, that cancels. That's just simply y equals 0. So we are inputting numbers on the x-axis. So in order to get real numbers out of this, I got to substitute real numbers into this. That's what that's basically saying. However, there is a point of exclusion. Because again, go back to the original function. You know, if z was equal to 1, I'd get 0 on the bottom of the fraction. Can't have that. So therefore, we can't input it. It's not in our domain. 1, 0. So locus is y equals 0. Okay. Another way of doing it, through geometry, if I play with the arguments. W is purely real, then I know the argument of W is either 0 or pi. So we're saying the argument of z plus 1 on z minus 1 is 0 or pi. What does this mean? Well, if I play around with it, argument of z plus 1 minus the argument of z minus 1. So the difference between these two arguments are either 0 or pi. Draw a little picture here. There's 1, there's minus 1. We're saying we want to place z in a position such that when I join them up to minus 1 and 1, their arguments are either the same, difference is 0, or differ by 180 degrees. So that'd be vectors going in opposite directions. So where on earth could I put it? Well, I can't put it above because they'll create different angles. It has to be on the line y equals 0. It's the only way I'm going to get either the arguments to be the same or in opposite direction. So there they are in the same direction, and then in between the two numbers, the vectors would be going in different directions. Minus 1 and 1 I have circled. Because I'm doing it via geometry now, we know that when we draw rays, we circle the starting point. That gives me 2 points of exclusion though, when originally I had 1 point of exclusion. So which one is it? Is it the first one where I only exclude 1, or is it the second one where I exclude plus or minus 1? You're going for the first one? Anyone else? Come on, be brave. You got a 50-50 chance here. All right, one person is brave. Why did you pick the first one?
Because you subbed the point into the original equation.
Right. Go back to the original equation. See, this is the correct answer if the question was the argument of z plus 1 on z minus 1 was 0 or pi. That would be correct then, because the starting point we can't have. Because argument, if I sub in minus 1, I couldn't have the argument of 0. Yeah? So for that question, fair enough. But the original question we asked, it does work. So again, you always go back to the original one and check. So answer the original question. Okay. Here's one of these arguments of, and I've got a linear function on a linear function. It's equal to pi on 6. Okay. So what we're saying is the difference in the arguments is pi on 6. Okay, there's my axis. There's a vector joining up to 0, so that's representing z. There's one joined up to 4, so that's representing z minus 4. You'll notice I've drawn it underneath rather than above. And I'll get to why I did that in a second. So what we're saying is the difference in these angles is pi on 6. That therefore means that the angle between them is pi on 6. So where they meet, that angle will be pi on 6 or 30 degrees. And you could prove that using a little bit of geometry. You know that the exterior angle is equal to the sum of the two opposite angles. So why is it below? Well, it's all to do with the size of the angle. Notice argument of z minus the argument of z minus 4 has to come up with a positive number. Has to come up with a positive number. Argument of z, which is this smaller number, but it's a negative number now, minus the bigger number, which ends up with a positive number. Right? So in reality, what I do with this is I try it above first and then go, oh, hang on, does that make sense? And if it doesn't, well, logic says it must be below that if it doesn't work. Okay, there's our position. Remember we said it was an arc of a circle. got to remember a little bit of circle geometry now to come up with this. So Z is moving on the arc of a circle. That therefore means the line joining 0 and 4 must be a chord of the circle. I put the midpoint in because we know perpendiculars from the centre bisect the chord. So this is how I'm going to locate the centre. I know I'm going to draw a perpendicular bisector to the chord. So there's 2. I know the centre has to be below. Pi on 6 means it's a major arc. So if it's a major arc, then the centre must be on the same side as that point of intersection. If it was a minor arc, then the centre would be on the other side. So I know it's below. I know the centre. Conveniently, the chord was horizontal, so I know that line joining the centre is vertical. So it has an x coordinate of 2. I now need to work out the y coordinate. Okay. Well, radius I can work out as well, because if 2y is the centre, then the radius must be the distance to the point there. So once I've worked out where the centre is, I can work out the radius. But then we remember another geometry theorem. The angle at the centre is twice the angle at the circumference standing on the same arc. So this whole angle at the centre will be twice the pi on 6. Pi on 6 is 30 degrees. So the angle at the centre is 60 degrees. So in this little right angle triangle, it must be half of that, 30 degrees. I think I've got enough information. Let's do some trig. Y over 2 is the tan of 60. So y would be 2 root 3, although it's below the axis, so I know it's going to be negative 2 root 3. So there's my centre. 2, negative 2 root 3. Let's do some Pythagoras. Work out the radius. The radius turns out to be 4. Okay, I finally got all the information I need to give an answer. I might have gone overboard with my answer, but here it is. Locus is the major arc of the circle x minus 2 all squared plus y plus 2 root 3 all squared equals 16, formed by the chord joining 0, 0 and 4, 0, but not including those points. Doesn't include those points, again, because they're the starting points of the arguments, so they're not included. In this case, go back to the original one, and it is saying argument of z on z minus 4. So both points would be excluded for that one. What's another way we could write that answer? Anyone got an idea? I'd still need the equation of the circle. I could, I guess, say, oh yeah. Yeah, we could talk about the range and say, but we're only interested when y is less than 0 or something like that. So that might be another way of writing that. How would you want to write it? Write it again.
Put it in the complex form of the circle. Or z is equal to?
I gotcha. You could write it as mod, what would it be? Z minus 2 plus 2 root 3i is equal to, that would be 4, wouldn't it? Yeah. So there's all sorts of different ways we could write our answer there. Okay. So, handful of questions out of 1F. Also, I only picked 2 out of 4 in from Patel. But the other thing I put there, which you might be interested to look at, is I've pulled out some of these geometrical sort of complex number questions that appeared in the HSC over the past. I forget how many years back I went, but there's a whole heap there you might like to look at.